Hello, ladies and gentlemen. You should be looking at lesson 10.5, which is over empirical and molecular formulas. So today we're going to learn how to calculate those and how to use them. So again, there's some bell work there that you can work through. That's a review of percent composition, which is important in order to be able to determine empirical and molecular formula. So make sure you complete that now. After you're finished, then we'll get into the lecture over our empirical and molecular formula. So what you should know how to do in this lesson is your first objective is you should be able to determine the empirical formula of a compound. Your second objective is you should be able to determine the empirical formula from percent composition data. And then your goal, the thing you should be able to do, is apply lab information, either information you do yourself in lab or information that's given to you, to determine the empirical and molecular formula of a compound. So let's get started. First of all, the empirical formula of a compound is the simplest whole number ratio of ions in a formula unit or atoms of each element in a molecule. So here's an example. So this is an example of a molecular formula. Okay? An empirical formula is, I'm going to simplify these numbers to the lowest they can do. In other words, what's the ratio of carbon to hydrogen? Well, 6 to 6 is the same thing as saying 1 to 1. I could divide both of these by 6 to get them to both be 1. So this would be the empirical formula of benzene, is CH. And it's because the carbons and hydrogens are in a 1 to 1 ratio. Here's another example of a molecular formula. This is octane, C8H18. Well, if I want to get the smallest ratio or the smallest subscripts on this, I can't divide them both by 6 again because they don't go into those numbers evenly. What I can divide both of them by, though, is 2. If I divide 8 by 2, I get 4. If I divide 18 by 2, I get 9, which means my empirical formula for octane would be C4H9. So these are empirical or molecular formulas. Molecular formulas are, how do these molecules actually appear in nature? Empirical formula is, what's the lowest ratio of carbon to hydrogen or whatever elements you're using in this compound. Here's how we calculate empirical formula. So how we calculate empirical formula is we actually usually need to be given percent composition data, which is what we went over in our previous lesson. If you need to kind of refresh on that and relook at it, you can go back and watch that video. So we can determine the mole ratio by having the mass data to find something like, say, radium oxide. So let's say we know we have radium oxide and we have a 1.64 gram sample of it. And we heat that compound. So we start with radium, okay? We start with radium metal. We know that we have 1.64 grams of radium. We heat it up and it gains mass. I know that might seem weird, but it actually does that. And now we have 1.755 grams of radium oxide. So what happened is we added oxygen to it. Now, how we find the empirical formula is we have to figure out, we know that we had 1.64 grams of radium, because that's how much radium we started with. Then we heated it and some oxygen got added. So we need to know how much oxygen got added. So what we do is we take our final mass, we subtract how much radium we know was in there, and that gives us the amount of oxygen. So now we know how much radium was there and how much oxygen was there. So we know the molar mass of radium and of oxygen. So what we're going to do is we're going to change those amounts to moles. So the first step is we need to find how many grams of each thing we have. We found our grams of radium. We found our grams of oxygen. The next thing we do is we change that to moles. So I change that to moles. When I change that information to moles, I get numbers that are really close to each other. In other words, the amount of moles of radium is just about exactly the same as the moles of oxygen. So here's what that means. We never use subscripts that are decimal numbers, but if we could, here's what my formula would look like. It's almost like I would have a subscript for radium that's 0.00726. That's because that's how many moles I have. And my subscript for oxygen would be 0.00719. That's because that's how many moles I have. Now, we don't write it like that with those tiny decimal numbers. But what we can do is we can divide by the simplest or the smallest whole number. So what we do is we take .00719, divide by both of those numbers, and we get relatively 1, the same number, which means the empirical formula of radium oxide is RaO. Okay? We'll walk through, I'll show you how to do another one. So there we weren't given percent composition data, but we were given composition data. Percent composition is what's the percentage of each element. Composition data is what are the masses, what's it made of. We were given composition data in the previous problem. What if we're given percent composition data? So what if we're told that we have 92.2% carbon and 7.83% hydrogen? Okay? And we want to find what its empirical formula is. Well, what we're going to do is we're going to assume that we have 100 grams. Just always, if you're not given grams amounts, just assume you have 100 grams. Okay? Because what that allows you to do is take these percentages, and now we can easily change those to grams. If I assume I have 100 grams of benzene, and I know that 92.2% of it is carbon, that means 92.2 grams of it is carbon. If I have 7.83% hydrogen, and I assume I have 100 grams, that means I have 7.83 grams of hydrogen. So by assuming we have 100 grams, it allows us to get our masses very easily. We could assume that we have 1,000 grams, but it would make our math a little bit more complicated. So really it doesn't matter how much you assume you have, but just assuming 100 grams makes the math easier. So now what we're going to do is we're going to calculate moles of each element. So the first step in any empirical formula problem is find your mass. Okay, if you're given masses, great. If you're given percent composition, then you assume 100 grams so that you can get to mass. Then you're going to change to moles of each element. So I'm going to take my grams of carbon and divide by its molar mass, or use dimensional analysis to get my moles of carbon. Then I'm going to take my grams of hydrogen, divide by its molar mass to get moles of hydrogen. Again, what this means is it means these are my subscripts. Well, these numbers are really, really close. They're about 1 to 1. Okay, 7.68 is about the same thing as 7.75. So what I would then do is I would divide each one by the smallest number. So notice how I'm going to take 7.68 and divide by 7.68. That's what I did here. I'm going to take 7.75 and divide by the smaller number, which is 7.68, and I get this C1H1.01. When you have numbers that are really close, you just assume that there's 1. So that means my empirical formula would be CH. Now if this was like 2.01, I would assume that it was 2, making this CH2. Now, what about a molecular formula? The empirical formula we said of benzene was CH. This represents the ratio of carbon to hydrogen atoms in benzene. So, but the actual molecular formula is actually a multiple of that. Remember we said that benzene actually isn't, its real formula isn't CH, it's something else. And we went over that previously in this lesson. So we know that benzene has a molar mass of 778 grams per mole. That would be information that would be given to you. So, and it says, find the number of times bigger that molar mass is than your empirical formula. So here's what you would do. You'd do a problem and you'd find the empirical formula. Then if it said, here's the molar mass of the molecular formula, find the molecular formula. Here's what you would do. You'd go, okay, I know I can find the molar mass of my empirical formula, the thing I just calculated. If it's CH, well, carbon's molar mass is 12.01, hydrogen's molar mass is 1.01. I get those and I get relatively 13 grams. Then I'd go, well, if the problem told me my molar mass of my compound should be 78, I'm going to take the molar mass of my molecular formula and divide it by the molar mass of my empirical formula. Here's what that means. That means that my molecular formula is 6 times bigger than my empirical formula. So what I'm going to do is I'm going to go through and I'm going to multiply each subscript by 6. So because it's C1H1, that means the real molecular formula for benzene is C6H6, which we learned that earlier. Now let's go over another practice problem. So on your notes page, it should say, have this problem. says a compound is found to have, by mass, 48.38% carbon, 8.12% hydrogen, and 43.5% oxygen. What is its empirical formula? So again, in your problem, whenever you're trying to find empirical formula, what you have to do is you have to find mass of each of your substances, then you have to change them to moles, then you're going to divide by your lowest mole amount to get your empirical formula. So in this problem, we're not given masses, we're given percents. So remember, when you're given percents, what's the thing that you do? That's right. You're going to assume that since there's no masses given, you're going to assume that there's 100 grams. So what that means is that each of your percents becomes grams. So in this previous problem, I had 48.38%. If I assume 100 grams, I'm going to have 48.38 grams. Then when I do it with my hydrogen, I'm going to have 8.12 grams and 43.5 grams. Then again, once we get our masses, we change the moles. So here's my dimensional analysis to solve for each of my mole amounts. So I'm going to take my grams of carbon, divide by its molar mass to get moles of carbon. Take the grams of hydrogen, divide by its molar mass to get the moles of hydrogen. Take the grams of oxygen, divide by its molar mass to get moles of oxygen. So now I have my mole amounts for each element. So the next step, okay, I've changed the grams first by assuming there was 100 grams. Changed to moles by dividing by the molar masses. Next step is now divide by the lowest mole amount. Okay, so I'm going to divide by my lowest mole amount. So my lowest mole amount from my previous slide was oxygen, which was 2.71 moles. So I'm going to divide each of them by 2.71, so 4.02 divided by 2.71, and I'm going to do that for all three of them. So I'm going to have 1.5 moles of carbon, 3 moles of hydrogen, and 1 mole of oxygen. Now, here's the issue. The chemical formula would be C1.5H3O. Well, remember how we can't have like half subscripts. So in order to remedy that problem, what we're going to do is we're going to have to multiply by a number, okay? We have to multiply each of these subscripts by the same number to get the lowest whole number of subscripts possible. So the number that I would have to multiply, in other words, what can I multiply a half by to get it to be a whole number? Well, that's 2. That's the lowest number I can multiply it by. So what I'm going to do is I'm going to multiply each of these numbers in my formula by 2. What that's going to do is get all of my subscripts to be whole numbers, because an empirical formula or a formula has to have whole numbers. So what that's going to do is that's going to give me this formula, which this is my empirical formula. My empirical formula would be C3H6O2. Well, here's another follow-up question. What if it said, okay, now you found the empirical formula, what's the molecular formula if the molar mass of the compound was 148.18 grams? So this is the one that we did with benzene a little earlier. So what I'm going to do now is I'm going to compare the molar masses of my empirical formula. Remember, my empirical formula was this, C3H6O2. I'm going to compare the molar mass of my empirical formula with the molar mass of my molecular formula. And how I do that is by dividing the molar mass of the molecular formula by the molar mass of the empirical formula. So the molar mass of my molecular formula was given to me, 148.18. I need to find the molar mass of my empirical formula, which was on the previous slide, which was the C3H6O2. So I found that molar mass to be 47.09. So when I do this, my molar mass of my molecular formula divided by the molar mass of my empirical formula, what I got was 2. Here's what that means. That means that my molecular formula is 2 times bigger than my empirical formula, which means I need to go through and multiply each of my subscripts by 2. So my previous subscripts was this. So I'm going to multiply each subscript by 2. That will give me my molecular formula, which means my molecular formula would be C6H12O4. Now, that extra step that we did, multiplying by 2 earlier, doesn't always happen. You only do that multiplying by 2 when you have a half of a mole in your compound, when you find the empirical formula. So when you have a half, again, you can't have that. So that's why we multiplied by 2 there. So again, our molecular formula should be this C6H12O4, and that would be our final answer for that follow-up question. Now, you could have had a question like this. What if at the very beginning of this problem, it had said, here's my information, what is the molecular formula? I would go through those same steps, but again, it has to give you the molar mass of your molecular formula so that you can compare it to get what you need to multiply your subscripts by. So that information, instead of doing like a follow-up second question, it could all be in one problem, just as another variation of that problem. So what you're now able to do is this ends our notes over empirical and molecular formula. So what you should be able to do now is you should be able to complete those problems at the bottom of your page. Again, just for some practice, there will be the answers will be provided for you. If you have any questions, make sure you let me know. Thanks for watching.